we present Leveraging Human Attention in Novel Object Captioning, a research by Xianyu Chen, Ming, Jiang, and Zhao from the University of Minnesota. Attention is an information selection mechanism that allows humans and machines to focus their visual perception and cognition resources on the most important visual input. Attention mechanisms have been developed for computer vision models to dynamically prioritize features. For example, driven by the success of deep neural networks and large-scale datasets, image captioners learn to generate descriptions of an input image. Attention mechanisms can help them focus on different regions when generating each word in the output. However, the success of image captioning methods has been inherently limited by the training datasets, typically designed with the focus on a small number of object categories, and they can't generalize to describe images with out-of-domain novel objects beyond the training data. To bridge this gap, existing works on novel object captioning use externally trained object detectors to detect novel objects and explicitly add them to the captions. For example, the constraint beam search method forces the inclusion of the novel objects into the output of a pre-trained image captioner. It is a test time method without requiring further optimization, which may sometimes lead to unnatural descriptions. In this work, to generate more natural and smooth descriptions of novel objects, we propose attention-based novel object captioner with two main contributions. First, we introduce human attention models to highlight generally important objects. Second, we propose a constrained self-critical sequence training approach that addresses the exposure bias when learning the description of novel objects. Human attention models trained on eye-tracking datasets can predict where people look in the image. They generate saliency maps where the saliency values indicate the importance of a given image region. They offer general knowledge to characterize what to describe about an image, which complements existing image captioners that emphasize object-level information. Therefore, using externally trained human attention models in image captioning can help generalize image captioners beyond the training data. Our proposed image captioner is based on the commonly used up-down architecture. It consists of a human attention pathway and a self-attention pathway. The human attention pathway incorporates features from a human attention model, which is static and task-independent, while the self-attention pathway learns to compute self-learned attention weights with end-to-end learning, which is dynamically predicted and can be different when generating different words. These two attention pathways highlight different visual features, and each group of features are fed into a language model to predict a caption. Finally, the two outputs are integrated through an adaptive gate. In addition, we propose a constrained self-critical sequence training approach that addresses the exposure bias when learning the description of novel objects. Image captioners are typically trained with a maximum likelihood estimation based on the sequential cross-entropy loss. Due to the contextual discrepancy between the training and evaluation metrics, the supervised learning strategy commonly leads to suboptimal evaluation results. Self-critical sequence training directly optimizes the test time evaluation metrics for image captioning, but it can't be directly applied in novel object captioning because it depends on a greedy sampling approach that doesn't guarantee the inclusion of novel objects. Our constrained self-critical sequence training method allows us to fine-tune novel object captioners on the in-domain data using test time metrics while considering the inclusion of novel objects. With these novel contributions, our method significantly outperforms the state-of-the-art novel object captioners on the no-caps dataset. We conducted a fair comparison by applying the same constraint beam search method to all the compared image captioners. The results of our method are significantly better than those of the state-of-the-art approaches in almost all of the evaluation metrics. In particular, compared with the state-of-the-art M2 transformer method, our method achieves 6.8% improvement in the overall CIDR score, which demonstrates that the captions generated by our method highly agree with the consensus as assessed by humans. Our method also outperforms the state-of-the-art method on the held-out COCO dataset, which is a subset of MS COCO, with 8 object categories excluded from the training set. In particular, we use the F1 score to evaluate whether each novel object is addressed in the generated caption of a corresponding image. The 5.6% improvement on the F1 score suggests that our method describes novel objects better. Our ablation study evaluates different variants of our proposed method. There are 3 baselines with only the captioner's self-attention, only the human attention, and the integrated method. There are also 3 improved methods by applying the constraint self-critical sequence training approach. From these results, we can observe that human attention itself can provide sufficient information for describing novel objects, which leads to a comparable performance with the captioner's self-attention. The promising result of combining machine's self-attention with human attention suggests that dynamically allocating the combination weights with the adaptive gate can effectively integrate the 2 attention mechanisms to generate better captions. Further, applying the constrained self-critical sequence training demonstrates consistent improvements in all the evaluation metrics. It can effectively boost the performance of novel object captioning by jointly fine-tuning the self-attention and human attention pathways with test time metrics. We present a qualitative comparison between our method and the baseline with only the up-down self-attention method and constrained beam search. These examples present the images, detected objects, regions, prioritized by the human attention model, and the generated image captions. We can observe that human attention can help in the novel object captioning task by paying attention to important objects missed by the object detector. It can also help to describe the scene with more details, to do better object counting, and to describe objects in a better order. These benefits from human attention significantly improve the diversity and specificity of the generated captions, leading to more natural descriptions of images with novel objects. To further demonstrate the effectiveness of human attention and the proposed gate mechanism, we visualize the 2 attention maps and the gate values that represent the weights of the human attention pathway. It can be seen that the gate values change significantly along the sequential prediction of image captions. The gate successfully learns to leverage human attention when the machine's self-attention fails to focus on the correct objects. Typically, the importance of human attention pathway increases when the self-attention fails to detect objects or object parts, or when describing semantic attributes and relationships between different objects. This suggests that the dynamic incorporation of human attention with self-attention can effectively make use of the 2 sources of information to improve the image captioning. In sum, our work proposes the first deep neural network model that leverages human attention in the novel object captioning task. It has 3 main contributions. First, we incorporate the human attention model to provide task-independent knowledge about important visual features that helps to prioritize the description of general objects in the image. Second, we dynamically combine the information from human attention and self-attention using a gate mechanism. Finally, we propose a constrained self-critical sequence training strategy to address the exposure bias while considering the inclusion of novel objects in the generated captions. With these contributions, our method has outperformed the state-of-the-art methods on 2 public datasets. Our source code is publicly available. For more details, please refer to our paper. Thank you.